Assalamu alaikum. I wish to welcome you to today's faculty development activity presentation. It is my pleasure and honor to have you on this platform despite your tight schedules. I'll try to make the presentation short and sharp. The title of my presentation is the polymer structure and properties relationship. That is, how structures of polymers affect their properties and also their application. My presentation will be based on the following points. I will start with the basics of polymer, that is the terminologies that are used to describe polymers, and then I will discuss about various classifications of polymers, and then the effect of structure on properties and application on common polymers. I chose common polymers because most of you are familiar with common polymers, and then the last will be effect of structure on the thermal transitions of polymers. The word polymer is a Greek word that is derived from poly, which means many, and then mass, which means unit. Thus, by definition, by meaning, polymers mean many units. For example, here we have this container contain many units of A, but these units of A's are not connected. And you remember that 1 mole of any substance, according to Avogadro's, contain about 6.023 times 10 raised to the power 23. This uh, implies many units, but under appropriate condition, these many units can react, combine together to form a chain, as in this case, which is called a polymer. And this chain contains many units of A that are connected together. So this is cannot be described as a polymer, despite the fact it contains many units, but this one has many units that are connected together, and this can be simply represented as A multiplied by the number of unit, which is n. So by definition, polymers are high molecular weight and long chain compounds that are formed by connecting small units together, and these small units are called the monomers. These monomers are the building blocks of the polymers. Therefore, monomers are compounds or small units that are connected together under appropriate condition to form a polymer. For example, if you look at this is an example of a monomer, which is propene or propylene, that it has a double bond. This monomer will react to form a polymer, and this will lead to formation of a long chain. This long chain can be shortly represented as a unit inside a bracket, which is the unit that is repeated along the polymer backbone, and this is called repeating unit. And the number of repeating unit is n here, which is called degree of polymerization. Now, in general, to what extent can you call a chain a chain to become a polymer? If, of course, if n is equals to 1, you have n is monomer. If n is equals to 2, you have dimer. If n is equals to 3, trimer, tetramer, pentamer, hexamer, and of course you have heptamer, octamer, nonamer. Now these ones are also contain many units of the monomer, but they are not long enough to be called a polymer. They are called oligomers. And oligo is also oligomer is also a Greek word that is derived from oligo, which means few, and mer means unit. So oligomer means few units. By definition, oligomers contain few units of monomers that are connected together but not long enough to be called a polymer. In some places, for you to have a polymer, n must be greater than equal or equals to 100, and in some places it is described as any molecule that have molecular weight more than 10,000 gram per mole. But when we talk about the molecular weight of polymers, we don't talk about molecular weight of, we talk about average molecular weight, because in reality, when you have a monomer, for example, you have here, you have 200 monomers represented by dots. Under appropriate condition, they give, for example, 10 chains. This 10 chain is called a polymer, just one polymer. So a polymer is made up of heterogeneous chain. chain with heterogeneous molecular weight. So in that case, we describe polymer molecular weight in terms of average molecular weight, which could be number average molecular weight or viscosity average molecular weight, which is determined from viscosity measurement. And then we have MW, which is weight average molecular weight, and then we have Z average molecular weight. But the most important ones are the MN and MW. So if you take the average of MW and MN, you get what we call polydispersity, which is polydispersity index. Now this index it gives you idea about the distribution of the chain. If the chains are of the same length, all the chains are of the same length, then PDI will be equals to 1, and the polymer is monodispersed. But sometimes it is usually more than 1. In most cases, it is more than 1. If it is close to 1, then it is called a polymer that is narrowly distributed. For example, the molecular weight are not far of the chain are not far from each other. But if you have a length that the polymer lengths are far from each other, for example, some of them are very long, some of them are medium length, and some of them are short, then you end up with what you call wide distribution molecular weight. All these are used to describe the molecular weight distribution of polymers. Now, the molecular weight of the polymer are often related to the properties of the polymer. For example, if you measure the viscosity, if you plot the graph of viscosity against the molecular weight of the polymer, the viscosity increases as the molecular weight increases. The tensile and impact strength, which are all mechanical properties, all increases until when it reaches a point where the increase in molecular weight does not affect the mechanical properties. So most of the polymers have molecular weight with average molecular weight within here. If the molecular weight is high, some properties will not increase dramatically, but the processing of the polymer becomes very difficult because of increase in viscosity. And when the molecular weight is low, it means that it is an oligomer, which will limit its application because it doesn't have enough strength to be used for some application. But not all properties changes because of increase in molecular weight. There are some properties like density, specific heat capacity, refractive index, and optical properties are all independent of molecular weight, which means that they do not change with increase in molecular weight. But properties like melt viscosity, solubility, chemical resistance, mechanical properties, they all depends on the molecular weight of the polymer. Now, I will be talking about the classifications of polymers. There are several classifications of polymers, but I'm going to discuss about some of these that I'm going to mention later on when I'm discussing about the structure, effect of structure on the properties of the polymers. The first classification is based on the origin, that is the source of the polymer. And here we could talk about either natural polymers, that is the polymers that exist in nature, or synthetic polymer that are produced in the industry. For example, natural rubber is a polymer that is derived from a tree, and this is called polyisoprene. You have cotton, which contains cellulosic material, and then you also have starch, which are derived from agricultural products. They are all called polysaccharides. And then you have the protein, which are called polyamides, and then you have DNA and RNA. They are all natural polymers. For example, DNA and RNA are called polynucleotides, and these are all natural polymers. Synthetic polymers examples are polyethylene terephthalate, which are used as bottle for water and soft drinks, PVC for pipes, and then you have polystyrene for food packaging, and then polypropylene for some of home applications such like crates, chairs, and other containers. These are all synthetic polymers that are produced in the industry. Another classification is based on the thermal behavior of the polymer. That is the behavior of the polymer when the polymer is heated. And in this case, we have two sub-classifications, which are thermoplastics and thermosets. Thermoplastics are polymers that melt when heated, and this can be remolded or shaped by melting and cooling. An example, for example, look at this candle here. When it's subjected to fire, it melts. And these polymers that behave like candle are called thermoplastic. Example are polystyrene, polyvinyl chloride, polycarbonate, nylon, and other polymers. There are some polymers that do not melt, that cannot be thermally processed, which means that they can not be remolded by heating. For example, when you take a paper, you put fire on paper. Paper do not melt; it decomposes. So polymers that behave like paper when heated are called thermoplastics. An example of melamine, which are example of thermoplastic elastomers like the tire. We have bakelite plastics, which is the phenolformaldehyde resin, and which have different application. This is also used for, it's a bakelite product. All these polymers are thermoset, which means that they do not decompose. Epoxy resins, they do not melt but decomposes when heated. Epoxy resins and unsaturated polyesters are all examples of thermosets. Another classification is based on the structure of the polymer. For example, you can have ethylene monomer, and ethylene monomer has carbon-carbon double bond CH2CH2, but under appropriate condition, it can lead to polymers with different structures. You can have a continuous arrangement of the atoms within the polymer chain, which is called linear polymer, or you could end up having a chain and then with an attachment, and these are called branch polymer, or you could end up with a cross-link polymer, and depending on the density of the cross-link, that will give you what we call a network polymer. So you can have polyethylene that is linear, polyethylene that is branch, polyethylene that is cross-link, and all of them have different properties and they end up with different applications. Classification based on composition within the polymer, that is, a polymer can be made from one type of monomer, and that is called homopolymer. For example, if A represents a monomer, then you can have a unit of a polymer that is formed from units of A that are connected together, A to form a polymer chain. And because they are made from one type of monomer, then it is called homopolymer. For example, polystyrene is made up of polystyrene, polyvinyl chloride is made from vinyl chloride, and then polypropylene is made from propylene, and polyethylene is made from ethylene. The repeating unit is just one type of repeating unit. As in this case, you have a polymer chain, and the repeating unit is vinyl chloride, so it is polyvinyl chloride. And sometimes you could have a polymer that is formed from two different monomers, or have two different repeating units. For example, if A represents one unit and B represents another unit, then there are four possible arrangements when you copolymerize two different monomers. You can have a situation where you have AB arrangement, and that is called alternating copolymer, or you can have a random arrangement where you have AA, which is called random copolymer, or you can have a unit of one unit connected together followed by another unit connected together. So you have block of A and followed by block of B, and this is a block copolymer, but this is an example of diblock. You could also have triblock. Another example, possible arrangement is you could have one monomer as the backbone of the polymer, and then the second monomer serve as a branch. So, and this is called a graft copolymer. So graft copolymer is a branch copolymer in which you have the backbone is one monomer, and the branch is another monomer, and all this will lead to a different polymers with different properties and also different applications. And the subclassification that is star polymer. This is an example of another copolymer, but specifically when we say star polymer, we mean polymers that are made from three different monomer. For example, this is acrylonitrile, this is butadiene, and this is styrene. So if you copolymerize all these monomers together, you end up with a polymer called ABS, and this is acrylonitrile butadiene styrene, which has different application in terms of home appliances, in terms of automobiles, toys, and also some of office appliances, materials like keyboards. These are made from a polymer. Now, the next classification, or the fifth classification I'm going to look at, is based on crystallinity, because the polymers are long chain, and they are long chain. This arrangement of chain can lead to different types of secondary structure. For example, you can have amorphous polymer, which means that the chains are arranged in a irregular fashion, and therefore they are called amorphous polymers. And amorphous polymers usually are inherently transparent. We're going to discuss about that. Example is polystyrene. If the polymer is arranged in a regular fashion, that is called a crystalline polymer. But we don't have a commercial polymer that is 100% crystalline. Most of the polymers contain regular arrangement and also irregular arrangement, and therefore they are called semi-crystalline polymers. And these polymers are opaque, they are not transparent. They're either milky, white, or cloudy. An example of that is polypropylene, polyethylene terephthalate, and polyamide. So this will also the percentage crystallinity will determine the applications of this polymer. We could also have classification based on commodity and engineering plastic. This is more of application. So commodity polymers are polymers that are produced in large quantities, high volume, and low cost, and therefore they constitute the one single applications of plastics, like for packaging, and they are not used for, sometimes they are used for durable application, but most of them are used for one single use application. For example, you have polyethylene, polypropylene, polyvinyl chloride, polystyrene are all example of commodity polymers. But engineering polymers are polymers that are durable, that are used for durable applications. They have superior mechanical and thermal properties. So they are produced in low quantity but low quantity, that is low volume, but the cost is high. And these polymers compete with metals, ceramic, and glass in various applications. And these are examples. They are used either in transportation, automobiles, trucks, and aircraft, construction, electrical, and electronics. They are durable, they are strong, and they are produced in low quantity. So they are called engineering plastics. The last classification, of course, is based on the mechanism, that is the method of polymerization. Some polymers are produced either by chain growth, that is addition polymer. They are called addition polymers, and these are mainly polymers that have multiple bond. Example, you have a double bond, they react to form a single bond, and these polymers are called addition polymers. For example, you have X here. If X is hydrogen, then it is polyethylene. If it is CH3 polypropylene, or polystyrene, polyvinyl chloride, polyvinyl fluoride, polyacrylonitrile, or polyvinyl acetate, all are example of addition polymers. The monomers contain double bond, and you end up with a polymer with a single bond. Now, some polymers can be produced by step growth mechanism, and these are called condensation polymers. And these polymers usually, in most cases, involve reaction of functional group. You have diacid, for example, will react to dialcohol to give polyester, and then water, small molecule, is eliminated during that such polymerization. For example, you have terephthalic acid and dialcohol, that is ethylene glycol, to give you polyethylene terephthalate, which is used as for as water bottle or a bottle for soft drinks. This is an example of condensation polymerization. Or sometimes you have diacid or acid chloride like cybaquel chloride and diamine with hexamethylene diamine will give you nylon, and this is called polyamide. And if it is cybaquel chloride, you end up with HCl as your byproduct. Now the HCl affects the polymerization reaction. So in this reaction, usually they add sodium hydroxide to neutralize to react with sodium hydroxide with the HCl that is generated through neutralization reaction. So these are all example of condensation polymers. So condensation polymers are example polyethylene terephthalate, polyester, polycarbonate, nylon. They are all example of condensation polymers. Now, having talked about various classifications of polymers, I will now move into effect of structure on the properties of some polymers. And I will start with the example of a very common polymer, which is polyethylene, where we find it everywhere at home, in the offices, everywhere we find polyethylene. Now, polyethylene is made from a simple monomer called ethylene, CH2 with double bond. Now, under appropriate condition, it will lead to polymer, which will lead to different polyethylene with different structure and different properties. For example, you can end up with linear polyethylene or branch polyethylene or cross-link polyethylene. Now, they all have the same repeating unit, which is CH2CH2. They are all called polyethylene. And this is represented, the linear is represented as high density polyethylene. We are going to discuss about why it is high density, and this one is low density polyethylene. We're going to discuss about why the density is low, and this one is XLPE, which is cross-linked polyethylene. We'll discuss about also the properties of cross-linked polyethylene. This is formed by addition polymerization and mainly using coordination polymerization using a catalyst. But in the case of this, in the case of branch polyethylene, it is produced also by addition polymerization, but in most cases, free radical addition polymerization. And then the last one is, of course, formed by chemical modification of polyethylene. So after you produce polyethylene, either linear or branch polyethylene, you can now use free radical initiator to cross-link the chain so that you end up with a cross-link polyethylene. These polymers have different degree of crystallinity. These are the different degree of crystallinity. The mechanical properties are also different. They have different mechanical properties. The melting point, they have we have gas transition temperature and crystalline melting temperature. We are going to discuss about those in details, but the melting point of these are also different, and we're going to discuss about that. And the linear polyethylene is called high density polyethylene, and it has a recycle code of 2, while this one has a recycle code of 4. But what is important here is these two are thermoplastic, that is the linear and the branch are thermoplastics, while the cross-link is a thermoset because the chains are connected through a strong covalent bonding. Now, let's look at the linear polyethylene. Linear polyethylene, for example, I have two chains of linear polyethylene here. These two chains of polyethylene, the chains are linear, but in most cases, they have short branches or complete linear. But what is important here is they can be packed closely. I mean, the chains can move very close to each other, and they have high density. Why do you have high density? Because the chains can be moved, can be packed, closely packed, and therefore they occupy smaller volume. And you remember we say density is mass over volume. So when the volume is high, then the density will be low. If the volume is low, then the density will be high. So in this case, because the chains can be packed together, they have low low volume, and low volume means high density. That is why they are called high density polyethylene. And of course, they have this arrow here indicate dispersion forces because they can move close to each other. They have high dispersion forces compared to the other polyethylene, and therefore they have high melting point, and of course they are strong and durable compared to low density polyethylene, and they are used for making plastic bottles and pipes. These are some of the applications of this of high density polyethylene. It is a bit strong compared to low density polyethylene. In the case of low density polyethylene, it is also a polyethylene but with branches. And once you have branches, then it will become very difficult to pack them together. So they are poorly packed. They are poorly packed, and because of that, you have void spaces, free volume here. That is why they have they have high volume, and high volume means they have relatively low density, and they are soft and flexible compared to high density polyethylene, because here you have dispersion forces, just few dispersion forces, and therefore they have lower melting point compared to high density polyethylene. They are used in application where flexibility is required, like plastic wraps, food packaging. You see, all these applications require flexibility. And for example, these hand gloves that we use these days during this COVID time, it is also made from branch polyethylene, which is low density polyethylene, and therefore this one, the recycle code is 4. So basically, the difference between high density and low density is in terms of branching. The more you have branch, the higher the volume and the lower the density. The last one is, of course, is the crystalline cross-link polyethylene. Cross-link polyethylene is represented as this. It is also poorly packed, so it has relatively low density because it also have free spaces, and it is hard and rigid because of the connection between the two chains. The chains are merely covalent bond, and it is a thermoplastic. Cross-link polymers are thermoplastics. They do not melt but decomposes when heated, and they are very strong, stronger than high density polyethylene, and therefore they are used as application where strength is required. For example, high voltage cable insulator, and also strong pipes. And in this case, this is an example of a polyethylene foam that is produced from cross-link polyethylene. So these are different polymers. These are the same polymer made from the same monomer, but under different polymerization conditions, you end up with different polymer structures, and these different polymer structures will give different properties that will determine the applications of the polymer. Now the next one we are looking at is the effect of secondary structure. And when we talk about the secondary structure, here we're talking about arrangement of polymer chain. And we can have, as I mentioned before, we can have amorphous polymer or semi-crystalline polymers. These amorphous polymers are usually transparent, and I've given you example: PVC, polystyrene, polymethyl methacrylate, acrylonitrile, butadiene, styrene, tar polymer, and polycarbonate. They are all transparent, and they are used where transparency is required. And here we have semi-crystalline. Most polymers are semi-crystalline. Polyethylene, polypropylene, but high density, low density. Cross-link polyethylene is a thermoplastics. It's a thermoset, sorry. And okay, here we have polypropylene, and then we have nylon. In general, these polymers are not transparent. They are opaque. They are not transparent. They are opaque, but we can make them to become transparent. So therefore, because of this arrangement, or because of these properties, amorphous polymers are they have irregular arrangement of chain, and they are inherently transparent. And they are used in application where transparency is required. For example, this is a feeding bottle. This is a PVC material. This is glass headlight of car, which is made from polycarbonate. We have greenhouse, we have the glasses. Our glasses, some of them are made from polystyrene or polycarbonate, and also you have this transparent jug, which is made from transparent amorphous polymer. And then, of course, we don't have polymer that is 100% crystallinity, but we have semi-crystalline polymers that are inherently not transparent. They are opaque, and they are produced in different degree of crystallinity. Example of those polymers are high density, low density polyethylene, polypropylene, polyethylene terephthalate. But as I said, some of these polymers during processing, for example, polyethylene terephthalate is semi-crystalline, which means it is not transparent, but you can make it transparent during processing. When you melt it, it becomes amorphous. When you quench it, you cool it immediately, then you end up with a transparent polyethylene terephthalate. But if you allow it to cool, normally that is annealing, then you end up with a semi-crystalline polymer that is not transparent. Now, since we are talking about transparency, let me just introduce you to optical properties. That is the optical properties of the polymer, which is measured in terms of absorption, light absorption, of measurement of the light absorption, reflectance, and transmission of light. So basically, when you have a light here, this is your polymer sample. When you subject the polymer to a light, what happens is you could have what we call reflection, and there are two types of reflection. The light will reflect at the same angle, and that is called specular reflection, or it could reflect at different angles, and this is called diffuse reflection. These two reflections are surface properties, are related to the surface properties of the polymer, because they are talking about reflection, and this is related to what we call Glox. Glox meter is used to measure these surface properties of the polymer. But the transparency is related to the transmittance, and transmittance can also be two. We can have a straight transmittance in which the light passes through the sample without changing the angle. It comes straight, and this is called a straight transmittance, and this is related to transparency. But it's possible that you can also have the light will pass through the sample but with a little deviation, and these are called diffuse transmittance, and this is related to haze, that is the cloudiness of the polymer. So the transparency of the polymer, which is calculated using this formula, would determine the applications of the polymer, and these are mainly, if you are talking about high transparency, this is related to amorphous polymer. And here you can have PMMA has transparency of 93, even more than the glass, which is 90. You have polystyrene, polycarbonate, and then polyvinyl chloride. All these polymers are used where transparency is required. So the higher the transparency, the lower the haze, that is the cloudiness. So you can measure the transparency in terms of haze or in terms of transparency. So most of these polymers, amorphous polymers, have high transparency. The next is the effect of tacticity, and here I've chosen also another common polymer, which is the second most common polymer, which is polypropylene. Polypropylene is a vinyl polymer that has CH3 as a pendant. Now, the arrangement of this CH3 within the polymer backbone can lead to three different orientation, which are called isostatic if the CH3 are on the same side. All on the same side, either all up or all down, that is isostatic, or if you have up, the next one is down, and this dash dash means down, up, down, then it is called syntiotatic polypropylene. And the last one, which is random, up, down, which is random arrangement, is called atatic polypropylene. Now, these are all examples, are all polypropylene, but different tacticity because of the arrangement of CH3. And these polymers are all produced from propylene monomer, but the Tacticity can be controlled using Ziegler-Natta catalyst or metallocene catalyst. Now we have several metallocene catalysts. Different industry use different catalysts, but to regulate or to control the tacticity. The first two, which is isostatic and syndiotatic, are stereoregular, and therefore they are rigid, they are crystalline, and they have high melting point and relatively low, relatively insoluble. While the last one, which is atatic, which is irregular arrangement of the pendant group, is soft, it has low melting point, easily soluble, and it is relatively transparent, which means it is amorphous. And therefore, the solubility is usually determined by what we call xylene solubility. So when they talk about xylene solubility, then you can now differentiate these different polymers. But these are different polymers that are made from the same monomer, but because of different arrangement, stereoregularity, they end up with different properties and different application. And this one, tacticity, is only for vinyl polymers like polyvinyl chloride, polystyrene, polypropylene, and polyvinyl acetate. But other polymers like that symmetrical polymers like polyethylene, which has a symmetry, does not have tacticity. Now, the next one is I'm going to discuss about the effect of copolymerization, that is on the properties of the polymer. And here I've taken a copolymer of a common polymer, which is ethylene, with vinyl acetate to produce a polymer called EVA, ethylene vinyl acetate monomer. Now, this amount of EVA, the co-monomer, will determine the properties of the polyethylene. So this one is just used to modify the properties of polyethylene for different application. And as you increase the amount of this vinyl acetate monomer, the low temperature strength will increase, impact strength will increase, transparency will increase, filler uptake capacity will increase, and weldability will also increase. But when you talk about the hardness, and melting point and barrier properties will all decrease as you increase the amount of the copolymer, which is vinyl acetate. And this EVA has different application. The EVA is produced by Sipchem. And also we have effect of copolymerization on viscosity. Now I've taken another monomer here, which is acrylamide monomer. Polyacrylamide monomer is a polymer. Polyacrylamide is a polymer that is used where enhancement of viscosity is required. That is, it is a viscosity modifier. So in some cases, if you want to increase the viscosity drastically, to say, you need to copolymerize acrylamide monomer with linear alpha olefin, and N could be any number, maybe, and this is why it is represented as this hydrophobe. It have hydrophobic property, and therefore it will lead to an increase in viscosity when you use few amount. In this case, they use few amount because this polyacrylamide is usually used in water, so the solubility will decrease as you increase the amount of the linear alpha olefin, which serve as hydrophobic. That is, it doesn't love water. So if you have this copolymer, you end up if you carry out this copolymerization, you end up with a copolymer that has hydrophobic part here, which will increase viscosity. How does it increase viscosity? Therefore, hydrophobic group under polymer solution, they can interact with each other and therefore increase the viscosity of the polymer solution. And that is why this kind of copolymer is used in application where viscosity, increased viscosity is required. For example, enhanced oil recovery, that is secondary recovery of oil. In this case, they inject high viscosity copolymer of polyacrylamide, which increase the pressure of the well, and therefore you can now take out the oil. You see, naturally, oil initially it comes out on because of the pressure build up on the ground, but after some times the oil is still on the ground, but the pressure is not enough to bring out the oil. So this is called secondary recovery. You have to use a method to recover the remaining oil, and that is called secondary oil recovery. And this can be achieved. One way is to use a very high viscosity polymer to achieve that. Now, the next thing I'm going to talk about is the thermal transitions in polymer. The thermal transitions in polymer usually involve the changes that take place when you heat a polymer. Now, let's look at example of, for example, you have a small molecules. For example, you have water, which is an ice, is solid, and when you increase the temperature, it will melt, it becomes liquid, and when you increase the temperature, it becomes vapor, and this vapor can condense to form back to the liquid, and then crystallizes or freezes and back to solid. And this is just for simple molecules, but of course we have some simple molecules like naphthalene. Naphthalene will move from solid directly to gas, and this is called sublimation. But in the case of polymers, we talk about semicrystalline polymer and amorphous polymer. At high temperature, these polymers, either of them will become the amorphous polymer will become soft and will end up as viscoelastic liquid. Also, semicrystalline polymer will end up as a viscoelastic material liquid as you increase the temperature, but we don't have gas polymer. So beyond this temperature, you are going to lose polymer, because polymer will decompose. So the cooling back will give you, if you cool back a semicrystalline polymer, you get back your solid. And also, if it is amorphous, you get back your solid. So if it is a thermoplastic polymer, you can remold it and reshape it and use it by playing with the temperature. So here, in the case of a polymer, we'll be talking about the temperature, the transition. And this transition are two transitions. It's either we have what we call glass transition temperature, the temperature at which the polymer becomes soft, or we have crystalline melting temperature, the temperature at which the polymer flow and becomes a liquid. Now, if you have, and this usually can be determined using specific volume, change in specific volume, which is the inverse of density as you increase the temperature. And of course, if it is amorphous polymer, you end up having only Tg. If it is a crystalline polymer, you end up with only Tm, because crystalline polymer have only regular arrangement, and therefore it has only melting point. But when you talk about semicrystalline that has both regular and irregular arrangement, you will have Tg and Tm, and usually Tg is always lower than the Tm for the same polymer. So you have Tg, increase the temperature, then you have Tm, and once you go beyond this region, then you break down the polymer will break down and decompose. And this another method that can be used to determine the Tg and Tm is differential scanning calorimeter, and this will give you, this is a typical example of differential DSC thermogram. Because of time, I may not be able to go into details, but in general, most of the polymers, the Tg and Tm values of the common polymers are provided here. And the polymers that are semicrystalline will have Tg and Tm. For example, polyethylene will have Tg and Tm. And when you look at polystyrene, the ones that are in red, polystyrene, polyvinyl chloride, polycarbonate, and polymethyl methacrylate only have Tg, no Tm, because they are amorphous polymer. And the knowledge of thermal transition give us are important when it comes to the selection of proper processing and fabrication condition for polymers. It is also used for the characterization of the physical and mechanical properties of the polymer, and of course these are also used to determine the temperature range for the applications of different polymers. But for the same polymers, the TG are usually lower than the TM. Now, we'll talk about another factor that affect the polymer properties called geometrical properties of polymer. I may need to be very fast because of time. We have geometrical effect is when you have the polymer, for example, we have polyisoprene. Polyisoprene could either be cis, that is when you have these two groups on the same side, or you have this should be CH2. Sorry, this should be CH2. You have this one or on the opposite side. So this is cis polyisoprene and this is trans polyisoprene. And this arrangement around the bond are called geometrical factor. And because they have different arrangement, which is cis and trans, you end up with different properties and of course different application. For example, cis as is soft, pliable, easily soluble, and it is used for making tires. While the trans, which is hard, is used for as a gold cover. It's tough and hard. So because of that, they have different, because of the arrangement, which is cis and trans arrangement, they end up with different properties and also different application. Now, let's quickly look at what are the factors that affect thermal transitions of the polymers. The first one is chain flexibility. So polymers that have, for example, CH2 groups are very flexible, while polymers that have benzene ring, for example, this one, benzene ring, are rigid. So the higher the higher the flexibility, the lower the TGA. So TGA decreases with increasing flexibility. So when you compare these two polymer, polyethylene terephthalate and polyethylene adipate, this one has benzene ring. Because of that, it is a bit, the flexibility will decrease and therefore it will have high TG. This one CH2, which increase flexibility, it has very low TG, but when you incorporate benzene ring into it, you end up with high TG. Similarly, when you have oxygen in the polymer chain, it gives you flexibility, and that will decrease the glass transition temperature. So the higher the flexibility, the lower the TG. Now we have some polymers that will have what we call intermolecular forces. For example, this is only olefin. It has only carbon hydrogen hydrocarbon polymer, which is polypropylene. But this one has Cl, which is highly electronegative. You have Cn, nitrogen is highly electronegative. You end up with dipole, and this dipole will make the polymer chain to interact. And once they interact with each other, they reduce flexibility. And reduced flexibility means high glass transition temperature. Similarly, when you have hydrogen bonding, for example, this is polyethylene. It has only CH2, but this is nylon. It has a functional group, and this functional group leads to hydrogen bonding. That is, the chains are connected due to hydrogen bonding, and that will reduce flexibility, and reduction in flexibility means high TG. That is why you have nylon TG, and it is used for strong applications, while polyethylene is soft. It has very low TG because there is, what the forces here are only dispersion forces, which is very, very weak, but in the case which is weaker than hydrogen bonding, and therefore the flexibility will decrease because of hydrogen bonding and TG will increase. Now we also have the polymers that have pendant group. As you increase the size of the pendant group, the flexibility, the TG will increase. For example, if R here is hydrogen, that is ethylene, it has very low TG. If you increase the size to CH3, which is polypropylene, the TG will increase. And when you move to Cl, benzene and naphthalene, when you have two benzene rings, the TG becomes very high because of the pendant group. Because once you have bulky pendant group, the bulky pendant group decrease flexibility and therefore increase TG. In the case of molecular weight, for the same polymer, if you increase the molecular weight, the TG will increase. For example, we have polystyrene here with molecular weight of 3,000, and here you have 300,000. This has TG of 999, and this one has TG of 43. And therefore, as the molecular weight increases, the TG will also increase, and this can be determined from this empirical Fox-Flory equation, which is given as TG is equals to TG of the infinite molecular weight polymer divided minus C, which is a Fox-Flory constant, divided by number average molecular weight of the polymer. The cross-linking also affect the TG and therefore also affect the application. For example, this is a natural rubber which is polyisoprene, and this polyisoprene is used to produce tire, and you can also use it to produce ebonite. If you have without sulfur, how do you make it? Tire is produced by the process called vulcanization. So you have polyisoprene, you add sulfur. The first sulfur serve as a cross-linker. It cross-link the polymer, then you end up with a tire. Now, if you have zero sulfur, which means there is no cross-link, then you end up the TGAs will be very low, because as you increase the cross-linking, flexibility will decrease and TG will decrease. Now, if you have 0.25, that is, you have little cross-linking, the TG will increase. If the cross-linking, if you increase the amount of sulfur to 10%, the cross-linking will increase, and then the flexibility will increase. So the TG will increase as the cross-link increases, because the flexibility decreases with increasing cross-link. Now, for tire, which is you need about 2 to 3% sulfur for vulcanization process, and if it is high sulfur content, which is about 30%, then you end up with this called ebonite, the one that is used for trucks and some it's a very strong, I don't know what they call it, but it's a wheel that is used for some trucks and some other devices, especially the children scooters. They are made from ebonite. Now, when we talk about the symmetry, symmetrical polymers usually have low TG. For example, symmetry reduces TG. For example, this is a symmetrical polymer, polyisobutylene, and polypropylene is non-symmetrical, because when you look at it here, if we put this line here, you have hydrogen on top here, you have CH3 down here, so it is not symmetrical. But when you have CH3 on top, if it becomes symmetrical, then the TGA will decrease, because symmetry increases flexibility and therefore decrease TG. Another example is vinyl chloride. Once you replace this hydrogen with another chlorine, you end up with polyvinylidene chloride, which is symmetrical, and because it is symmetrical, it becomes more flexible. More flexibility will decrease the TG. And here you have 87, and here you have minus 174. We have talked about geometrical factor, where you have cis, this is on the same side, and then you have trans on the opposite side. And we said the double bond decreases rotational barrier. When it is cis, you end up with a higher TG than when it comes to trans, because cis has higher TG because it has lower TG because it reduces the rotational barrier and therefore increases the TG. Tacticity. We have discussed before that tacticity polymers could be, vinyl polymer could be syndiotatic and atatic or isotatic. And in general, if you have the same polymer, for example, we have polymethyl methacrylate, which could be syndiotatic, atatic, and isotatic. Syndiotatic usually have higher TG, which is followed by atatic, and then the last one is isotatic. Copolymerization and polymer blending. Usually, when you copolymerize, the TG will affect the TG, and blending will also affect the TG. Copolymers are polymers that are made from two monomers by reacting two monomers together. Polymer blendings are polymer is a mixture of two different monomers. So each either copolymerization or polymer blending will lead to a change in TG, and this can be determined using this empirical this equation. Similarly, plasticization, that is an additives, usually we have some polymers, you add some additives to a polymer to make them flexible. For example, PVC, this is flexible PVC in which you added plasticizer to make it flexible, and this is rigid PVC. And because of that, you end up with having polymer with different TG, the same polymer PVC, and here you have rigid and flexible. The flexible one usually have low TG, and this can also be determined depending on to what extent you want to modify the flexibility. You can use this equation to determine the amount of plasticizer that will give you the polymer with the desired TG. In conclusion, this brings us to the end of the presentation. In conclusion, we can say that polymers are versatile materials that are used in wide ranges of application, and they have characterized by primary and secondary structures. Primary structure, we're talking about linear, branch, cross-link, and the second structure, we're talking about amorphous, semi-crystalline, and crystalline. And most of the structures can modify to achieve desired application, and most of the structures affect the properties and of course the applications of the polymer as we have presented. We have thermal transitions in the polymer, which are TG and TM. These are important properties of the polymer, and there are several factors that affect thermal transition of the polymer. And at the end, there is a strong relationship between the structure and the properties of the polymer. And this brings me to the end of the presentation. If you have any question, you are free to go ahead, please. Assalamu alaikum wa rahmatullahi wa barakatuh.